Good morning, everybody, and thank you for inviting me to co-chair this webinar 1.2 about the rules for new buildings in Eurocode. So I am Gabriele Milani from the Technical University of Milan, and will co-chair this webinar, sharing the co-chairing with Professor Jean-François Semblat and from the Institut Polytechnique de Paris in France. And I would like, before starting the presentations, to give you some rules regarding the questions and answers session. It is a live question and answer session, and which will follow each presentation. We will be in charge to moderate the questions and answer section. So all the questions, if you have questions, should be written directly in the chat. You can write your question either during the presentation of the speaker or immediately after the end of the speech by the presenter. But please make sure that before making the questions or formulating the questions, make sure to identify yourself, writing in the chat your name and surname plus the affiliation. We will collect all the questions, and then in the session, questions and answers, we will forward them to the speakers. Please remember that the total time that is allotted for the Q&A session is 10 minutes. And overall, the presentation of the speakers will be time framed in 35 minutes, and exception made for the last presentation that is short. So let's go immediately to give the floor to the first speaker, that is Professor André Plumier from the University of Liège, Belgium. And the title of the presentation is General Overview and New Futures. So please, Professor Plumier, the floor is yours, and you can share your presentation. Thank you.
Thank you, Mr. Chairman. Well, my presentation is on the general parts of Eurocode 8, part 1.2, and pointing out some new features which are present in those parts, in those chapters 5, 6, 7 of 4, 5, 6, 7 of this part 1.2. So part 1.2 has 15 chapters, a total of almost 400 pages, and the chapters on materials will be presented, so 10 to 15 will be presented in the next webinars, by the next presenters. This part also has 13 annexes, 7 being normative and 6 informative, with the list which is there. And most of these annexes are completely new or rewritten sections in comparison to the previous version of Eurocode 8. In my presentation, the new features in comparison to Eurocode 8 of 2004 will be in blue color. Now, sorry, but I'm okay. So this is a way to point out the new features, but I keep, let's say, the usual data in black color, so for the completeness of the presentation. Now, in the revised Eurocode 8, 4 limit states are envisaged: operational, OP, damage limitation, DL, significant damage, SD, and near collapse, NC. For buildings, the only mandatory verification are for the significant damage limit state. Now, of course, the national annex or the contract may ask different things. For most structures, this non-exceedance of SD state avoids exceedance of near collapse under a more severe action, and damage limitation exceedance under a seismic action less severe than that of design. In the revised Eurocode 8, there are, like in the previous one, 3 ductility classes, DC1, DC2, DC3, but their definition is partly different from the DCL, DCM, DCH of the current Eurocode. DCL is very much the same as DC1, but the limits of application of DCL, now DC1, are revised. I will explain that later. DC2 is a new class in which local overstrength is enforced by capacity design and plastic deformation criteria, but the control of global behavior is by limitation of drift, and of second-order effects. There are thus in this DC2 no criteria like the weak beam strong columns, which was imposed in DCM. DC3 is very much the same as former DCM or DCH, depending on the material. So it's like DC2 with criteria for global plastic mechanism and like a weak beam strong columns or else. The reference seismic action, there was a complete explanation about seismic action in webinar 112. But I mentioned that the reference seismic action is now the plateau of the spectrum. So it's the maximum 5% damp response spectral acceleration, the constant acceleration range. And this is for a 475 years earthquake return period on site category A and consequent class CC2, which is defined in the table up there. So PGA, the former reference parameter, is S alpha 475 divided by FA, which is in general taken equal to 2.5. Response on sites other than A for consequent class other than CC2, apply a complete formula there in which you see appear factor for soil site FA, but also factor FT for topography, and then the gamma limit state consequent class. And for damping other than 5%, a factor eta is applied. Now, these are data for your information. I will not speak about these tables, but this is just to make the slides complete for your use. A new parameter is also introduced, is the seismic action index S delta, very much the same to the S alpha mentioned before. Delta takes into account the influence of consequent class, and the other 3 factors, FA, FT, and S alpha, are as mentioned before. This S delta is used in many places in the code to define the seismic action class, so low or moderate or high seismic action class, and also to define limits of seismic action for given structural types per material and per ductility class. Now, there has been an evolution of this S delta from the current Eurocode of 2004 to this revised one. In 2004, in DCL, there was a recommended limit all types PGA 1 meter per second square, which correspond to S delta equal to 2.5. But in the revised Eurocode 8, these limits are mandatory values of S delta. And for instance, for non-ductile type, well, the value of 2.5 meter per second square is kept, but for other type, it's a significantly increase up to 5 meter per second square for walls and metal structures. In DC3 and DC2, there are mandatory limits which are given by chapter, as will be explained later. Conceptual design, well, the classifications of structural types are extended in all chapters by materials, and besides of the basic types, there is more distinction between different dual types and their relative contributions of the types. There are new types like flat slabbed or steel lightweights, and also general clauses about hybrid structures in which two or more structural types and or material are present in the same resisting plate. Also, an important step for usage is that the design for strength with force reduction factor, now named RQ of T, equal to 1, so-called Q equal 1 clause. Well, such design is allowed, in particular if it applies if a ductile behavior can hardly be conceived for certain structures, for instance, concrete or steel domes, and also if non-dissipative design can be safe and economical, for instance, with steel K-bracing or truss beams and columns. Concerning primary and secondary seismic members, the definitions, of course, are the same, but there is one new clause to allow the way to neglect or to take into account the presence of secondary members. It is in the case if the contribution to lateral stiffness of all secondary members is smaller or equal to 30% of that of all primary members, then two analyses are performed, one only with the primary, a second with primary and secondary, and the most unfavorable effects from 1 and 2 are considered in the verifications. So the usual way, which was to have a stiffness contribution less than 15%, is kept, but there is this new possibility. Concerning the characteristics of buildings, the way to qualify buildings as torsionally flexible, new ways are introduced, which can be detected directly out of results of model analysis. It's the case if in each main horizontal direction, the greatest effective model mass is not the one of the first or second mode, or alternatively, if the period of the first predominant torsional mode is greater than the period of the predominant translational modes in the two main directions. So this is a serious help for designer. Now, of course, the general criteria to qualify a building as torsionally flexible are kept and are similar to what exists in the current Eurocode. Concerning structural regularity, for in-plan regularity, there are no longer rules. There is only guidance because it's considered that the analysis of the structure takes into account the in-plan irregularity, if any. Regularity in elevation requires continuous resisting system and progressive variation of mass, stiffness, and resistance over height with the numbers which are mentioned there. And this is the fact to be regular gives some advantage in certain verification, as I will show later. Concerning modeling, basically the things are the same, but there is a limitation to the use of two planar models in the modeling of a structure. This is allowed only for low-rise buildings. Height less than 10 meters is very high, 1-story high, and less than 15 meters for 2-story high. The way to consider crating is kept the same with 0.5 times the stiffness of the uncracked member, if unless better estimates are justified. Concerning eccentricity, concerning torsion, there is a significant difference between the revised Eurocode 8 and the current one, and it is in the way to take into account eccentricities. So there are two eccentricities distinguished. One is the natural eccentricity, being the distance between gravity and torsional centers. And there is a minimum design eccentricity imposed. Now, in the force-based approach, the way to introduce moments of vertical axis in the structure is to consider a certain eccentricity but now it's the maximum in between the natural one and the minimum design eccentricity. And also the amplification factors, which could be used for simplified, to simplify life, well, they are now deleted, and they were very, very penalizing. In 3D models, you have the same. The addition of the natural eccentricity and the minimum design eccentricity is no longer practiced, and it's the same as in force-based analysis. There is a contribution of the natural and the minimum design eccentricity, but never the addition. Now, in response history analysis, story mass are such that the eccentricity is greater than the minimum one defined by the codes. For modeling and structural analysis, this has been completely explained in webinar 113. So for force-based approach, nothing new, but there are sections of the revised code about displacement-based approach, as I will mention later in this speech. Another thing which I recall, which was presented also, is that the behavior factor Q is now divided in the contribution in 3 contributions, one being QR, which is the overstrength due to plastic redistribution of seismic action effect in the progressive yielding stage, so alpha U over alpha 1. QD express the capacity of deformation and energy dissipation under constant yielding of the structure. QS take into account overstrength due to all other sources. So Q equal QR time QS time QD, and in chapters by material, default value of Q, QR, and QD are given, which I recall are upper bounds per material, structural type, and ductility class. Concerning the behavior factor you are allowed to use in the force-based approach, you have a certain number of clauses with reduction in case of non-regularity, what to do in case of 2 different systems in 2 different directions with different Q factors in 2 directions, etc. So these rules are basically the same as in the current Eurocode. The lateral force method of analysis is now forbidden for structures of high elevation, so higher than 30 meters, or with the first period of the first mode greater than the minimum of 4 TC, TC being a corner period of the earthquake response spectrum, design one, or 1.5 seconds. And for the definition of the period of the first mode, the way to establish it as defined is the code, is the relay one, in which the formula of T1, which is there, is used, with S being the displacement in meter of the ice story under a gravity applied horizontally. Approximate formula are allowed if justified by background, but they are no longer given in the code. Response spectrum analysis, well, was explained in a previous webinar. I do not insist on it. Concerning nonlinear static analysis, there again, this was explained in detail before. I just mentioned that in the case of low-rise wall buildings, if the bending moment effects in walls are low in comparison to shear action effects, each story may be analyzed independently. The revised code provide in this part 1.2, like in part 1.1 and in the other parts, data for the practical usage of nonlinear analysis. For nonlinear static analysis, all these clauses in blue are given to allow the construction of the capacity curve. So I will not give details on this. This is the way to calculate the normalized lateral force and the way to apply it to the structure and where to apply it and where to check the control displacement of the structure. Correction factors are given, which are ratio between normalized deformations obtained from the linear elastic analysis and from pushover analysis. They have variations, one in plan, one in elevation of the building, and they primarily account for torsional effect and higher mode effect in elevation. For response history analysis, I suggest you go back to webinar 113 or to the revised Eurocode 8 itself. Verification at the significant damage limit state in the force-based approach. Some basic verifications are exactly identical to what exists in the current Eurocode. Equilibrium, the building should be stable, including overturning or sliding. Action effect should be smaller or equal to strength, or strength should be greater. This can be expressed in terms of force, but also in terms of displacement. So generalized strains, interstory drift member chord rotation. And in such case, for the data on chord rotation, you can go back to part 1.1, where you will find graphs of this nature for every type of material. So there is a description of local mechanism which is given, and the current data are summarized in this slide. But I do not insist not to duplicate what is explained in these webinars. Now, one significant difference is about the control of second-order effects in the force-based approach. On this graph, you see a force displacement curve of a structure and the horizontal loading representing an earthquake. And you have here the expression of the sensitivity coefficient theta of the code. Now, in 2004, this was P tot time relative displacement at SD state divided by V tot times the story haze. So GRD equal Q dis type D. However, the problem there in this expression is that V tot does not correspond to SD state. You have V tot 2004, which is here. And what is done with this expression is in the revision process is to bring this shear force to the level of significant damage force or resistance. So the revision means that the force here at the denominator is now QR QS V tot, so that theta globally gives smaller values than in the past. Yeah. Now for the checks related to theta, the let's say battery of formulation is kept. So if theta is smaller than 0.1, it's okay. Between 1.1 and 0.2, you have to multiply seismic action effect by 1 divided by 1 and minus theta. Second order analysis, if theta between 0.2 and 0.3 and not allowed above 0.3. In the displacement-based approach, which is new in this code in comparison to the current Eurocode, well, there is no problem with the formulations of theta because it's the first time there is such an expression. The code expresses limits of interstory drift at the SD limit state. So it's not like in the past when it was at the OP limit state. So there is a general expression that the relative interstory drift should be smaller than lambda s times hs, where hs is the story haze. But the difference is that there is no need to calculate action effects at the operational limit state in addition to the SD limit state. The limitation of interstory drift are tuned to fit at SD limit state with the expressions which are here. Now the lambda value are given in chapter 10 to 15 per building structural type and material. Capacity design in DC2. As I mentioned before, there is no longer the application of global plastic mechanism criteria like webbed beam strong columns. Prevention of soft story is realized by limitation of drift and of second order effects. And for some types of structure, there is no further verification required than complying to these limitations. So it's the case for concrete wall systems or concrete wall equivalent dual systems, dual with concrete or steel or composite structure. For moment resisting frame and moment resisting frame equivalents, if they are regular in elevation and respect the limit of S delta and of interstory drift, well, all these require no further verification than these limitations. Now, in DC3, where you get the advantage of higher behavior factor, the verifications to do are similar to those of DCH of the current Eurocode. Concerning the horizontal diaphragms and horizontal bracings, there is a clause which requires overstrength of this part of the structure. Same with the foundations and data for foundation and underground basement. They are no longer present in part 1.2. They have been presented as part of part 5 of the revised Eurocode. The conditions on seismic joints are unchanged in comparison to EC8 from 2004. Now, another significant difference in the revised cost in the introduction of a column axial force amplification factor omega. So now the reason for that is explained here. The analysis by a force-based approach gives the action effect, moment, axial force, and shear in columns. First, plastic hinges suppose a case in which they happen at the basis of the ground columns. Well, they take place for a certain total applied load V1, which is Q as V tot. And in that stage, you have an equilibrium here, which is expressed by this equation here, which includes the axial force in columns NEDE and the plastic bending resistance of the base of the columns. Now, the global mechanism is obtained under VU, which is QR times V1, so that the real axial force in columns at SD is greater than the calculated NED under V1. And this is why there is a need to introduce an amplification factor omega. Now, omega is the ratio between this NED real and NED from the analysis. Now, you can calculate it here in this small example, but a number of tests on different structures has shown that this factor could take as a standard value omega equal to 2. So it means the seismic action effect is amplified by a factor 2 in comparison to what is present in the current Eurocode. This can be seen here. The NEDE refer to this point of the curve force displacement, whereas the NED real is here because NED keeps increasing to resist the overturning moment in the structure after the stage in which NEDE is realized. In the code has been introduced to the request of SEN more explicit clauses about force transfer zones in DC2, DC3. These are zones where vertical components of the primary structure are interrupted for open spaces, car parks, or setback. They should be designed with overstrength and using this expression in which there is an amplification of the effects of all nature calculated in the transfer zone, omega d being a ratio of resistance to action effects in the dissipative zone above the transfer zone, and an amplification factor 1.25. The model for such transfer zone required that there be a 3D model in which the structural members of the transfer zone are explicited, and the analysis should be at least response spectrum, or it can also be 3D nonlinear. It is mentioned in the code possibilities to realize strengths of these transfer codes. 3 possibilities are mentioned, which are all gathered in this drawing here, where you have the transfer zone at this place. So it can be realized by a diaphragm at the level of interruption, plus a beam in the plane of the wall, plus support by columns in the same plane, by a couple of horizontal forces in 2 diaphragms, this is here, or by column in the plane of an interrupted wall, this is here. So it's a case which mixes different possible interactions. Behind this is the need to have an idea of which is the plastic mechanism which is aimed at SD. And there is no application of weak beam, strong column in the tempo zone because this one is designed to remain elastic. There is also in the code a huge section, 13 pages, about ancillary elements. There is already something in the current Eurocode. There is an explanation on how to calculate the seismic action effects on these ancillary elements using this expression here of FAP. Now, the main modification is about SAP, which was given by a simplified formula in the current Eurocode. Now, SAP in general terms is the value in the flow acceleration spectrum for T period of the ancillary, and CAP, damping of the ancillary. Now, different ways are open to calculate this SAP. If flow spectra are available, well, you read this value of at AP at G's floor on these spectra. If they are not available, there is a more complex, more complete and improved formulation of way to calculate this SAPG by this formulation here. So all details are given to calculate this expression, which is a serious improvement in comparison to the current Eurocode. If this applied for rigid ancillary elements, if not rigid, and a criteria to qualify this rigidity is given. If not rigid, SAP can be calculated according to a method given in Annex C. The design of frames with interacting masonry hidden fields is a subject of other limitation of drift than those strictly applied to the frame. They depend on the masonry infill time following the table which is shown here. If there are openings, the limits are reduced. If there are confinement or reinforcement, they are increased by the factors which are given here. The analysis of frames with infill may be made in different way. One way is with a model of the bare frame only, and this applies if the distribution of infills is quite regular. For this reason, a horizontal regularity parameter has been introduced, which take into account the symmetric character or not of the infills present in the structure and their distance to the axis of the structure. And this is for both X and Y direction. Now, if the building is regular enough, simplification are possible. But if it is irregular, the infills have to be modeled explicitly. Concerning vertical irregularity, the method present in the current Eurocode is CAPE with this factor K1R given and which you know. Concerning the explicit modeling, infill may be modeled as struts, and there are values given in the code concerning the way to calculate the strut stiffness, the width of the struts, their thickness, and their modulus. If there are openings, there is a factor which can be calculated. I will show later. Explicit requirement concerning the verification of columns adjacent to infills are given. They are partly based on the length of columns over which the diagonal strut force is applied, which is a result of the definition of the struts I just showed before. And for the rest, the clauses are similar to what they were, in fact, in the current Eurocode. Now, concerning interacting infills, the verification in plane, well, first are on drift demand being smaller or equal to drift capacity defined in the table shown before, and shear action effect calculated as explained here, as shown here, should be smaller or equal to design resistance calculated according to Eurocode 6. If there are openings, there is an expression to calculate the factor rho OP, which takes into account the geometry of the infill and of the opening, and all the values used are shown here are given in the table. For the verification out of plane, the lateral action is calculated based on the same FAP value with this expression. Resistance may consider flexural or arching effect resistance as calculated in Eurocode according to Eurocode 6. But the condition is that this, let's say, reduced strength should, the action effect should be smaller or equal to 0.5 the flexural or arching resistance of Eurocode 6, and this 0.5 is a, let's say, rough way to take into account the interaction between in-plane and out-of-plane action effects. And also conditions are given concerning the connection of infills to bounding frame. For non-interacting infills, explicit conditions are given to allow to limit the contribution of infill to lateral stiffness and to limit the interaction between infill and frame up to a drift demand at SD. Now, the connections should accommodate the design interstory drift at SD. The code also includes explicit requirements for structures with claddings. They concern in particular their connection, which can be of the isostatic type or of the integrated type, which means they contribute in such case to interacting claddings. And clauses bear also on connection of these integrated panels. And the similar developments are made for partitions where requirements are explicitly given in the code. Now, this concludes my presentation, and I'm happy to answer to some questions. Thank you. Thank you for your attention.
Thank you, Professor Plumier, for your exhaustive presentation. I have collected 4 questions by the attendees. So, starting from the last one, is the question coming from Federica Vadala, University of Minho, and she's asking the following question. Could you please explain why in the new generation of the Eurocode, the elastic response spectrum has constant SC for T lower than TA?
So maybe I should show.
Yes, if you need to reshare the part of the presentation, then please act on your Zoom platform so you can share the presentation.
Okay, so the question is why
in the new generation of the Eurocode, the elastic response spectrum has a constant SC for T lower than TA? Smaller than TA.
I think it's not clear. The limitation, well, the way to express the stiffness in this range is not reliable to the point. This response itself is not, let's say, sufficiently reliable in reality that you can have immediately a curve. Now, I must say that the definition of this spectrum was made not by PT2 but by PT1 and was explained in the previous webinar. So I confess that I don't have the exact answer to this question, which we should transmit to the members who prepared this webinar 1.1. So sorry, I cannot say more.
Okay, thank you. So let's go to the second question. This is a question by Sébastien Semeleni, who's an expert at technical direction of Socotec. And he says, I have a question about the calculation of the 2 models for primary and secondary elements. Stiffness of secondary elements needs not to exceed 30% of the primary, and we have to do 2 modeling calculations. One model with primary and the other with the secondary plus primary, and take the most unfavorable effects. But the response of the 2 models to a seismic excitation are not the same. How could we compare the values for the 2 models?
Well, is this one?
Do you want to share for you, André? Because I have it open here.
So this is the slide. Huh? No, this is not the slide. This is it.
Do you want me to share it? I have it open. You are not sharing, André.
Sorry. Okay, now I think I'm sharing, okay?
Yes, you are. Yes, correct.
Well, I think this is a way to find a worst case situation. So the question is about this B, so this new clause about a way to do in case the lateral stiffness of secondary, taking into account secondary members, the lateral stiffness contribution is less than 30% of all primary seismic members. So please, could you repeat the questions now that we have the slide here?
Yes, sure. The question is the following: is stiffness. I have a question about the calculation of two models for primary and secondary elements. Of course, it's not my question. It's a question by Sebastian.
Yeah.
And stiffness of secondary elements needs not to exceed 30% of the primary, and we have to do two modeling calculations. One model with primary and the other with secondary plus primary, and to take the most unfavorable effects. But the response of the two models to a seismic action are not the same. How could we compare the values of the two models?
Well, you can compare the action effects. They are results of the two analyses.
Okay. So I would like to go.
But I understand the point. The question, in fact, is what justifies to do so?
Yeah, correct.
Now, let's say that these are two extreme cases which can represent the situation. So there is an upper bound and a lower bound, and the reality is necessarily somewhere in between these two bounds. And the way to be safe is to consider the worst case of action effects, but they are not the same structure. This is, I agree. And of course, the problem with such a definition is that you also need to do two analyses and compare. So the work is amplified, say, but it's already the case. Just to define the fact of the first condition, there you have to see to make the analysis with and without the secondary members. But I think the second condition, well, it has been checked that doing so, you are on the safe side. And so this is written in terms of a clause in order to, let's say, open a little clause in comparison to clause A, which was felt too restrictive.
Thank you, André, for this exhaustive answer regarding this tricky question. So unfortunately, I have to say that we are running on delay, so I have to stop the Q&A session, and we have to go ahead with the other presentations.
Okay, and, thank you.
So I leave the floor to my co-chairman, Jean-François. So, the floor is yours, so you can present the second speaker.